Good morning, boys and girls, and welcome back. Today we are going to talk about improper integrals with infinite discontinuities. Usually in class, I have you start with this warm-up question. So I can say, pause the video and try to do this integral. Now, if you really paused the video like you were supposed to and worked it out, I'm guessing you did something a little u-sub like this, and you ended up getting an answer like -2. However, this answer is incorrect because what we have going on right here, if we think about this graphically, is there's an asymptote at x equals 1. We have a picture that looks something kind of like this. And because we have the asymptote at x equals 1, we get what we call an infinite discontinuity there, okay? Because we're approaching the asymptote from two different sides, all right? And we need to account for that. We haven't had to worry about that yet. We've maybe done problems like this, just we went from like 2 to 5 or something like that where we didn't have to worry about the asymptote. But now you're going to have to start watching out. If you have a vertical asymptote, we're going to have to deal with it. We're going to have to split things up. And that's what we're going to talk about today. All right, quick little review of a topic from yesterday. We talked about the integral from like 1 to infinity of 1 over x or 1 over x squared. And we talked about when those things would converge or diverge. And here's kind of our rule for it kind of summed up for us. If I'm looking at the integral from 1 to infinity of 1 over x to the p, where p is some power, if that p is greater than 1, I know that it is going to converge. If the p is less than or equal to 1, I then know that it will diverge. And if it does converge, I actually even have a formula. 1 over p minus 1 will be what it's going to converge to. So like 1 over x squared converged just as we showed to 1, because 1 over 2 minus 1 is 1. All right? So quick little rule. We're going to, again, when we get into series, we'll talk more about that. But just a review of that topic from yesterday. And now kind of applying a little bit more to today's stuff. If I look at the other side of 1, we are looking at, if we look at the other side of 1, we're looking at where we approach the x-axis now. This side right here, kind of. From 0 to 1 or 0 to some number, we're looking at that space in here. And this actually has like a flip set of rules. If p is greater than 1 or equal to 1, that's going to diverge. And if p is less than 1 now, that area in here, that area in here is going to converge, right? When p equals 1, notice it always diverges. 1 over x diverges in both directions, right? 1 over x squared will converge as we go to infinity, but it'll diverge as we approach 0, okay, as we approach that asymptote. And so we're going to kind of, we'll use that a little bit today as we talk about as we're approaching asymptotes. All right? Notationally, here's how we're going to have to phrase things now. All right, if I'm doing the integral from a to b, and there's an infinite discontinuity, or a vertical asymptote at b, okay? As I'm coming up, it's at the end of my, it's at the end of my interval, okay? If it's at the b value. Then we would say the limit as c approaches b, but we're going to say from the left because I'm approaching from the left, okay? Limit as c approaches b from the left of a to c f of x dx. And so that's how I'd have to notate this correctly. If it is on the other side, if we are talking about, if as I'm approaching from this side here, say, right? Then we would be where the integral is starting. So the a value, and it would look something like this. The limit, or the integral a to b of f x dx equals the limit as c approaches a from the right if the infinite discontinuity or the vertical asymptote is on the left-hand side of your interval, and then the integral from c to b of f x dx. Those would be the proper notations given a vertical asymptote. All right, so let's give this a go. Okay, so we're going to look at the integral from 0 to 1 of 1 over x to the 1/3 dx. Using our rules of that 1 over x to the p, because we're going from 0 to some number, and my p is less than 1, we should know that this is going to converge. It's just now what matter, what is it going to converge to? So let's evaluate and find out. So because we have a vertical asymptote at x equals 0, and that's where my limit is at, I would first start with the proper notation, limit as c approaches 0 from the right, since it's at the beginning one, and I'd rewrite this as x to the -1/3, and now I can integrate. Add 1 to the exponent, and I get x to the 2/3, divide by 2/3. I'm really going to multiply by 3/2, so I just kind of skip a step there, so I get the limit as c approaches 0 from the right of 3/2 x to the 2/3 evaluated from c to 1. So this gives me the limit as c approaches 0 from the right at 3/2 1 plus 2/3 minus 3/2 times c to the 2/3. And then when I evaluate this limit, 1 to the 2/3 is 1. 1 to the thing is 1. So 1 times 3/2 is 3/2. And then first try substitution. If I plug in 0, 0 to the 2/3 is 0, times 3/2 is 0. So we end up with just getting 3/2 minus 0, or just 3/2 is what this is going to converge to. Okay, next one. Integral 0 to 1 of 1 over x dx. Again, we have a vertical asymptote at 0, so this is our improper integral with an infinite discontinuity. Similar to the last one. Again, if we're thinking about our x to the p rules, 1 over x to the p rules, we said when p is 1, that is always going to diverge. So this should diverge. And now, again, let's go and show it. Again, using proper notation, I should get the limit as c approaches 0 from the right of c to infinity of 1 over x dx. When we take the antiderivative of that, I get the limit as c approaches 0 from the right of ln of absolute value of x, evaluate from c to 1. Or when I evaluate it, I get the limit as c approaches 0 from the right of ln of 1 minus ln of c. ln of 1 we know is 0 minus ln of c. Again, I can't take the natural log as 0. I can't plug in. But I can think about if I'm going to attack ln of 0 from the right, ln functions look like that. And so if I approach 0 from the right, then I'm approaching, I guess, negative infinity. So I get, if I'm thinking about it, again, there's all kind of an analytical, evaluation of our limit. But I get 0 minus a negative infinity, or this is then going to go to infinity. So, like we said, oh, cool, that is going to diverge then. That is not going to converge on a number. That is divergent. Okay, so getting to a better example here. Again, kind of like our warm-up problem. I want to do the integral from 0 to 2 of x minus 1 to the negative 2/3. All right, so when you have stuff like this, I think the very first thing we should do is to rewrite it. And I think you want to rewrite it like this to, again, make yourself cognizant to the fact that this is going to have a vertical asymptote. This would have a vertical asymptote, again, when the bottom equals 0. So there's going to be a vertical asymptote at x equals 1. And so because that vertical asymptote occurs on my interval from 0 to 2, I now need to be careful, and I'm going to have to split this thing up and deal with approaching this asymptote from the two separate sides to see if it's going to converge or diverge as we approach this asymptote. And so we're going to want to evaluate these two integrals separately, okay? Now, when we do this, if they both converge, then this converges. However, if either of them diverge, then it is divergent. So one can diverge, or they both might diverge, but if either of them diverge, then it is divergent. So to sum that up, it converges if both converge, but it diverges if either diverge. All right, now let's work on our integration of this. Again, in this case, my asymptote is, the vertical asymptote is on the right-hand side, and then on this one, the vertical asymptote is on the left-hand side. So let me rewrite these using the correct notation. Okay, so on the first one, because the asymptote is on the right-hand side, I need to approach 1 from the left of that integral. And on the second one, because the asymptote is on the left-hand side, then I need to approach 1 from the right. Again, if you think about this graphic, I think it helps me set it up. And I know this is kind of tedious and a pain, but this is the proper mathematical way to set these up. So now when I integrate this, again, add 1 to the exponent, becomes to the 1/3, divided by that power. Again, because it's x minus 1, I don't have to worry about any chain rule, so I don't really have to use u sub. So I get 3x minus 1 to the 1/3, evaluate from c to 0, or 3x minus 1 to the 1/3, evaluated from c to 2. All right, and now I'm going to go ahead and use the fundamental theorem. Okay, and I split it up a little bit here, but I get the limit as c approaches 1 from the left, 3 times c minus 1 to the 1/3 minus 3 times 0 minus 1 to the 1/3, plus the limit as c approaches 1 from the right, 3 times 2 minus 1 to the 1/3 minus 3 times c minus 1 to the 1/3, and now I can evaluate these limits. In this case, we can do direct substitution, and when I plug in, 3 times 1 minus 1 is 0, 0 to the 1/3 is 0, so I get 3 times 0 minus 3 times negative 1 to the 1/3. Negative 1 to the 1/3 is negative 1. So negative 3 times negative 1 gives me 3. Plus, then I do this one here. 2 minus 1 to the 1/3. 2 minus 1 is 1. 1 to the 1/3 is 1. So I get 3 times 1 minus, and again, if I plug 1 in here, 1 minus 1 is 0. Times 3 minus 0. Or I get 3 minus 0, or 3 plus 3 is 6. So in this case, because they both converge, this converges, and it converges to 6. Awesome. That was kind of fun. And going back and just double checking, kind of going back to our x to the p thing here, that we opened up our discussion with. This was 1 over x minus 1 to the 2/3. And so because, again, that was a number smaller than 1, and we're approaching that infinite discontinuity of that vertical asymptote, that makes sense that this converges. I know it's a little tricky, but I like to kind of think about that as a way to kind of check myself when I'm doing my work, or try to anticipate what the answer is. Again, after 5 years, I'm just now starting to do that, so I know that might be a lot to ask at the moment. But if you're feeling comfortable with that x to the p stuff, I do think it helps to kind of, check our answers a bit. All right, moving on to number 4. The integral negative 1 to 2, 1 over x cubed dx. Okay, so first thing here I'm thinking is, I got to watch out. I've got a vertical asymptote at x equals 0, and 0 is on my interval, so that's something I'm going to have to be aware of and deal with. And again, going back to our previous conversation, because this is to the 3rd power, I'm thinking this probably should be divergent. But now I'm going to go and prove it and show it and just double check myself and make sure. So, step 1, split it up at the asymptote and write your 2 different integrals, and then you're going to rewrite it using the proper notation. So, the limit as c approaches 0 from the left, since your asymptote is on the right, at the end of your interval, you got to approach from the left. Negative 1 to c, x to the negative 3rd dx, plus the limit as c approaches 0 from the right, since the asymptote is on the left-hand side now. I'm going to approach from the right, c to 2, x to the negative 3rd dx. Then I'm going to take the antiderivative, and I get negative 1/2 x to the negative 2nd. And then I need to evaluate this using the fundamental theorem of calculus. And we get that step right there. The limit c approaches 0 from the left, negative 1/2 c to the negative 2nd, minus negative 1/2 negative 1 to the negative 2nd, plus the limit c approaches 0 from the right, negative 1/2 2 to the negative 2nd, minus negative 1/2 c to the negative 2nd. I need to work on my spacing, I think, a little bit. It looks like 2 spaced out here, 2 close there. But I'll work on that on the next problem. And then now I'm going to evaluate this. If I plug in, if I look at this, this is negative 1 over 2 times c squared. And if I approach 0 from the left, this is going to become a small number, right? And so negative 1 divided by a really small number is going to go to negative infinity. This is going to be negative 1 to the negative 2nd is like minus negative 1/2 over negative 1 squared. So this is going to become, negative 1 squared is positive 1, so negative times negative is plus 1/2. And then plus, same thing here, as I approach 0, I'm going to get, let's see here, I get negative 1/2 over negative exponent over 2 squared. So this is plus negative 1/8. And then here, same thing. And I guess really I probably could stop right now because I see I've got this negative infinity. But if I evaluate this one back here, I'm going to get plus 1 over 2 times c squared. And again, really small number, so plus infinity. And so this thing here, again, infinities are not all the same size. Those infinities do not kill each other off. If I've got infinities there, one might be bigger than the other, but this is going either to infinity or negative infinity. So this thing does diverge. It is divergent. All right, boys and girls, that is today's lesson. If you got questions, hit me up. Otherwise, see you later and have a great day.